Right now, as you watch this, part of your life is passing through a building you will never see. A windowless fortress of steel, cables, pumps, transformers, and fans is remembering for you, calculating for you, predicting for you. And that raises a question that sounds like science fiction until you look closely. Will civilization eventually move part of its mind off Earth? Because the cloud is not a cloud. It is a factory. A data center is a factory for computation, storage, and switching. It takes electricity in, turns that electricity into calculations, stores memory on hardware, and moves information from one place to another at astonishing speed. It is less like a library floating in mist, and more like an industrial district whose product is thought. And if you follow that thought honestly, something strange happens. You begin on the ground, with ordinary things, concrete pads, diesel backup generators, maintenance crews swapping failed drives at 2 a.m., cooling towers drinking water, substations humming, fiber lines entering the site like arteries. But then the intuition arrives almost all at once. If these places are so hungry for energy, so demanding of land, so entangled with water and heat, why not move some of them into orbit? There, above the weather, sunlight is abundant. There are no neighborhoods next door complaining about noise. There is no real estate board, no zoning hearing, no storm surge creeping across a parking lot. So the dream expands in real time. Orbital server farms, lunar data vaults, AI clusters hanging in cislunar space, watching the Earth and the Moon like silent librarians of a planetary civilization. The internet becoming, quite literally, extraterrestrial. And before we go any further, we need to ask the question correctly. Not, can we put computers in space? We already do. Satellites compute. Spacecraft process signals. Probes navigate autonomously. The real question is sharper. Can space host meaningful, economically useful, scalable compute infrastructure? And if so, what kind? To answer that, we have to strip the romance away and keep the wonder. Every data center, whether in Virginia or vacuum, must solve the same 6 survival problems. Power in, heat out, data in and out, hardware that keeps working, physical maintenance when things fail, and a reason to exist that is strong enough to pay for all of the above. That list sounds dry until you realize it is really a list of civilization's dependencies. We like to imagine the digital world as weightless, but almost everything precious about modern life now leans on physical systems that can break. Your bank records, medical scans, navigation systems, weather forecasting, scientific archives, the invisible machinery of governments and markets. It all lives somewhere, and where it lives shapes what is possible. So let's run a thought experiment together. You have to place the next critical piece of humanity's digital memory somewhere safe from storms, war, rising energy demand, and the fragility of geography. Do you bury it underground? Do you float it at sea? Do you place it in orbit? Each answer feels attractive for about 10 seconds. Then the hidden costs emerge. Underground gives you protection, but not immunity. Flooding, geology, politics, access, and cooling all return. At sea, you gain modularity and isolation, but corrosion, logistics, storms, and cable dependence tighten around you. In orbit, you escape some terrestrial burdens and inherit alien ones. That is the pattern we will keep seeing. Every escape from Earth trades one set of constraints for another. And here is the first major audit finding. Public conversation often treats space as if it were one location, one condition, one answer. But space is not a place in the everyday sense. It is a spectrum of environments with radically different costs, temperatures, radiation levels, communication delays, and service possibilities. Low Earth orbit is not geostationary orbit. Lunar orbit is not the lunar surface. Cislunar space is not just farther away. That matters because the first viable generation of space data centers, if they emerge, almost certainly will not be floating replacements for the cloud you use to store photos or stream video. The strongest near-term case is narrower and more powerful. Compute placed near the place where data is born. In other words, orbital edge compute. If that phrase sounds technical, picture a kitchen instead of a supply chain. Edge compute means you do some of the chopping, sorting, and decision-making close to the source before sending the finished portion farther down the line. In space, that could mean a satellite constellation generating oceans of raw imagery, radar returns, signals intelligence, navigation data, or scientific measurements, then processing the most valuable fraction before transmission to Earth. And now we step into the machine room of reality. This is where seductive headlines usually lose their footing. Because every server is a heater that happens to think. That line is not a joke. It is the core physical truth. A processor consumes electrical energy to perform computation, and nearly all of that energy ends up as waste heat. On Earth, that is hard but familiar. You move air. You circulate liquid. You use heat exchangers, chillers, cooling towers. You place the facility near dense power infrastructure and thick fiber connectivity. And when a component fails, a technician drives over and replaces it. In orbit, intuition betrays you. Space is cold, yes, but cold is not the same thing as helpful. A winter night on Earth cools your skin because air and moving fluid carry heat away from you. That process is called convection. Think of convection as heat hitchhiking on matter. In vacuum, there is no surrounding air to carry your heat away. Your spacecraft must shed heat mainly by radiation. Radiation is heat leaving as light, mostly invisible infrared light. Imagine trying to cool a busy kitchen not with fans or water pipes, but by making the walls glow their heat into darkness. It works, but not quickly, and not cheaply. To reject a lot of heat, you need large radiator surfaces. And large radiators are mass, structure, deployment systems, vulnerability, complexity. This is where many space data center fantasies hit their first wall. If you scale compute upward, waste heat rises almost with it. The thermal problem does not politely remain in the background. It moves to the center of the stage and starts giving orders. So ask yourself, if you launched a powerful orbital computing platform tomorrow, what would grow faster, the processors or the surfaces needed to cool them? That is not just an engineering detail. It may be the decision point between a useful system and an orbital monument to wishful thinking. Power creates the next layer of temptation. Sunlight in space is strong and constant over portions of an orbit, so at first glance the case seems easy. Endless clean solar energy, problem solved. But abundance in principle is not availability in practice. To feed large compute loads, you need solar arrays, deployment mechanisms, power management electronics, batteries or other storage for eclipse periods, pointing control to keep the arrays oriented, thermal management for the power system itself, and enough structural integrity to survive launch and operations. Even a modest terrestrial data center can consume power on the scale of megawatts, and large ones can demand far more. Reproducing even a tiny fraction of that in orbit is not a trivial extension. It is a different category of machine. Every kilogram you launch carries opportunity cost. Every additional subsystem multiplies failure pathways. And then there is latency, the one constraint people invoke both too much and too little. Latency is delay. Not just distance, but the total waiting time in a network path. Fiber on Earth is spectacularly good. It is dense, mature, reparable, and already woven through the regions where users live and businesses operate. If your customers are mostly on Earth, serving ordinary cloud workloads from orbit means fighting not just physics, but a century of terrestrial infrastructure accumulation. Low Earth orbit helps compared with more distant regimes. It reduces communication delay. It can support broad coverage. But links still require handoffs, line-of-sight geometry, weather interactions at ground stations, and the choreography of moving nodes. You are not replacing a quiet buried fiber route with magic. You are replacing it with a dynamic network in motion. So what applications survive that audit? The ones where data already originates in space, where immediate local processing creates value, and where sending everything raw to the ground is wasteful, slow, or impossible at scale. Think of Earth observation satellites taking relentless images of oceans, forests, cities, fires, ice sheets, shipping routes, crop stress, methane leaks. Think of military systems watching for missile launches or tracking fast events that matter in seconds, not hours. Think of space domain awareness platforms trying to distinguish meaningful motion from a blizzard of orbital clutter. In those cases, on-orbit compute is not a vanity project. It could become the difference between drowning in data and extracting intelligence. But there is another enemy above us, silent and impersonal: radiation. Space is not merely empty. It is electrically violent. Charged particles from the sun and from deeper cosmic processes can strike electronics and flip bits, corrupt memory, trigger faults, or degrade materials over time. A single event upset sounds small, almost polite. In practice, it can be the digital equivalent of a neuron firing when it should not. That means reliability engineering becomes central. Redundancy, error correction, fault tolerance, hardened components, autonomous management software that can isolate failures, reroute tasks, and recover from anomalies without a human walking into the room. On Earth, many failures are inconveniences. In orbit, they can be endings. And if a board fails in a terrestrial data center, the repair chain is ordinary. Detect, dispatch, replace, reboot. In orbit, the equivalent may involve no repair at all, or a robotic servicing mission, or an architecture designed from the beginning to tolerate module death as a normal event. This is where launch cost enters with false simplicity. Yes, launch has become cheaper. That is real, historic, and important. But lower launch cost does not erase the requirement that everything you send must survive vibration, shock, vacuum, thermal cycling, contamination control, and long-duration operation without easy human touch. Space hardware does not just need to work. It needs to deserve the journey. Now slow down with me, because this is the point where dream and reality almost touch. The dream says, no land costs, no local water stress, clean solar power, physical isolation, resilience against some terrestrial disasters. Reality answers, launch is expensive, servicing is hard, heat is stubborn, orbital debris is real, and every kilogram must earn its existence. Orbital debris deserves that pause. We are not placing delicate machines into a pristine cathedral. We are adding them to a contested, crowded shell around the planet. A future with more valuable orbital infrastructure demands better tracking, avoidance, disposal, and active stewardship. The more computation you place up there, the more you care about the traffic ecology of near-Earth space. And then the paradox deepens. The best reason to compute in space may not be to serve Earth users directly at all. It may be to support space systems themselves. That single shift changes the whole picture. Suddenly, we are no longer asking whether orbit can compete head-to-head with hyperscale terrestrial cloud regions for your everyday app traffic. We are asking whether orbital platforms can do filtering, sensor fusion, encryption, compression, anomaly detection, autonomy, and scientific analysis right where the measurements appear. And under that framing, the idea stops looking absurd and starts looking almost inevitable. Imagine a constellation generating petabytes of imagery each day. Petabytes so large they cease to feel like human quantities and become weather systems of information. If an orbital compute layer could reduce that flow by a factor of 100 before downlink, preserving the useful signal and discarding the redundancy, the economics shift dramatically. Now flip it again. Imagine trying to build a 50-megawatt orbital data center to mirror terrestrial practice. You do not launch just servers. You launch power generation, storage, radiators, shielding, structure, communications equipment, attitude control, navigation, fault management, and a story about maintenance convincing enough to survive the first board failure. Which subsystem explodes first? For me, the answer is not singular, and that is the point. Heat fights you. Power fights you. Maintenance fights you. Network economics fight you. The dream breaks not because one law forbids it, but because several truths quietly align against the wrong architecture. That distinction matters because possible is one of the most misleading words in technology. Almost anything is possible if you are willing to overpay, underspecify, ignore maintenance, and confuse demonstration with deployment. The deeper question is fitness. Does the system belong there? Does physics reward the placement, or merely tolerate it? And this is exactly where the audit has to contribute something constructive. We should not just say no to grand claims. We should identify the hidden threshold where yes becomes rational. Here is the theoretical hypothesis I find most compelling. There exists a mission density crossover point where orbital edge compute becomes not just useful, but inevitable. It appears when data generation scales faster than downlink capacity, and when mission value depends on near real-time inference or prioritization. That is the frontier problem. Not whether space compute is cool. Not whether one demo can be launched. The real unsolved question is where the crossover sits for different mission classes. Earth observation, missile warning, space traffic coordination, autonomous satellite networks, scientific monitoring. And that hypothesis is testable. Build a mission-agnostic model with variables for sensor output, downlink bandwidth, inference urgency, onboard power availability, acceptable error rates, and the value of acting early rather than late. Then apply it across use cases. If the model predicts that onboard processing repeatedly lowers total mission cost while increasing mission utility, the case strengthens. If not, the idea retreats into niche status. There is a second hypothesis worth putting on the table, because thermal constraints are so dominant. Instead of designing orbital compute for continuous operation the way terrestrial facilities often are, we may get better performance per kilogram from burst mode architectures. Compute hard during the moments of highest mission value. Store heat temporarily in phase-change materials. Schedule workloads around orbital conditions. Let the platform breathe. If phase-change material sounds abstract, imagine ice in a cooler, but engineered for spacecraft temperatures. It absorbs heat during periods of intense work by changing state, then releases that heat more slowly later when the radiators can catch up. Pair that with intelligent task scheduling, and a smaller system might deliver more useful mission output than a larger one trying to run continuously. That, too, is falsifiable. Launch a small demonstrator. Instrument the thermal loops. Compare sustained operation to burst mode processing over many orbital cycles. Measure useful process data, radiator mass efficiency, power draw, and degradation. Let hardware, not hype, decide. And then there is robotic servicing, the quiet wildcard. If in-space servicing becomes routine enough, the economics shift again. A compute node that can be upgraded, repaired, or refueled is not the same asset as a sealed machine waiting to die. Suddenly modularity matters more. Interface standards matter more. Replaceable accelerator boards matter more. Could that rescue the bigger orbital data center vision? Maybe in part, over time, for specialized systems. But even there, one truth remains stubborn. Cheap power in space does not automatically imply cheap compute in space, because thermal rejection may continue to dominate the architecture. And beyond Earth orbit, the conversation gets even stranger. Could the Moon host archival storage? Could cislunar infrastructure support navigation, science, or sovereignty-driven compute nodes? Could deep space missions rely on distributed processing farther from Earth? Perhaps. But communication delay grows teeth there. Servicing grows harder. Economics narrow. What emerges, if we are honest, is not a story of relocation but of differentiation. The future is rarely an old system moved wholesale into a shinier setting. More often, progress divides labor. Earth remains the dense, reparable, fiber-rich heart of computation. Space becomes the frontier layer, sparse, specialized, autonomous, and valuable precisely where distance changes the rules. That is the answer hiding beneath the original mystery. Space data centers are not nonsense. They are just frequently imagined in the wrong shape. What is dream, at least in the near term, is the idea of giant orbital cloud regions replacing mainstream terrestrial hyperscalers for ordinary consumer and enterprise workloads. Physics does not forbid it forever. Economics and engineering simply refuse to reward it yet. What might be here soon is more modest and more revolutionary. Small to medium orbital compute platforms attached to missions that already live above us. Processors that filter remote sensing data before downlink. AI inference engines that detect anomalies, prioritize events, and compress what matters. Secure mission-specific compute nodes for resilience and defense. Hybrid architectures where the first urgent pass happens in space, and the deeper analysis stays on Earth. That hybrid model may become one of the defining infrastructures of this century. Not because it sounds futuristic, but because it respects physics. It places each kind of computation where its constraints are most naturally met. Bulk processing where power, cooling, people, and fiber are abundant. Immediate local decisions where the data first appears and delay is expensive. And there is something quietly profound in that. We began with a question about server racks in orbit. We end with a broader lesson about intelligence itself. Minds, whether biological or technological, survive by distributing labor wisely. The eye does not digest. The stomach does not see. The brain does not pump blood. Systems thrive when function meets the right environment. So picture the closing image clearly. Earth below, bright and turbulent, carrying the massive reparable industries of computation. Orbital nodes above, lean and alert, handling what only proximity, autonomy, and perspective can handle. Not rivals. Organs in one larger technological body. And now we can synthesize the audit in one clean line. The mystery was never whether space can host computation. It can. The real question was where space compute actually fits. And the answer is this, not as a wholesale escape from Earth, but as a specialized extension of civilization's nervous system. Carry one thought experiment with you after this ends. The next time you upload a file, ask yourself where that act truly belongs in the physical universe. What part should happen in a building near a river and a fiber trunk? What part should happen above the atmosphere, close to sensors watching the planet in real time? If intelligence can be distributed across layers of reality, What does that say about the future shape of human presence itself? And the next great question opens right there. If we do not move all computation into space, but only the forms of computation that gain meaning from distance, autonomy, and vantage point, then what other technologies are waiting for the same realization? If you made it this far, stay with the investigation. Subscribe if you want rigorous audits that separate physics from spectacle and turn frontier ideas into clear reality checks. On the end screen, watch the next video, because it extends this same chain of questions one layer deeper. And in the comments, give me your simplest answer to this. If you had to trust one critical system with humanity's future, would you place it underground, underwater, or in orbit?